All right, lads and ladies, welcome back to Calc 2. Today we're going to continue our recent exploration into integration techniques. Specifically, we're going to look at section 7.2 on trig integrals. This is really not a new method. Most of the sections in chapter 7 introduce an entirely new method. This one is an exception in that really we're just looking a little more closely at a certain family of integrals, all of which fall to existing methods. But let's take a look at this, and you'll get to see what I'm saying. So today we're going to talk about trig integrals. Which is section 7.2. Right, so last week we talked about integration by parts, which is section 7.1. This week we're doing trig integrals, and I might introduce a little trig sub at the end of the week, but mostly today is just integrals of trig functions. The reason we're doing this right now, and the reason this comes before section 7.3, which is trig sub, is because in section 7.3 we're going to learn some tricks for taking integrals of algebraic functions, those are like polynomials and square roots and stuff, and turning them into trigonometric functions. There are some special substitutions you can make that take non-trig integrals and turn them into trig integrals. So we want to be really good at trig integrals so that we can handle those. Those turn out to be very, very powerful techniques, trigonometric substitution. So 7.3, think of this whole section as kind of preparation for section 7.3. Some prerequisite knowledge, we will freely use the following identities. The following trig identities. If I use anything that's not from this list, I'll explain where it's coming from and all that, but things from this list we will use often. Sine squared plus cos squared equals 1, and its various forms like sine squared equals 1 minus cos squared equals 1 minus sine squared. This is called the first Pythagorean identity. The second Pythagorean identity, tan squared plus 1 equals secant squared, and all of its various forms like tan squared equals secant squared minus 1, or secant squared equals 1 plus tan squared, all those. There's another form of this, which is 1 plus cotangent squared equals cosecant squared. You'll need these in some of the homework problems, but I won't be working many problems which require this because really they're symmetric. They're the same as this other thing. So anything that works for secant and tangent works for cosecant and cotangent too. This whole family of identities is called Pythagorean identities. Then you have what are called double angle identities. Sine 2x equals 2 sine x cos x. I'll refer to this as the double angle identity for sine. There's a couple of double angle identities for cosine. If there's one that you should keep in your head, it's this one. And then the other two versions of the double angle identity for cosine can be found by substituting the first Pythagorean identity equivalent in for any one of these. So this is the only one I'm going to write down right now. And then there's also some half angle identities, and we'll use these a lot. The half angle identities look like this. Cos squared x equals 1/2 times quantity 1 plus cos 2x. This is called a half angle identity because the thing over here, the x, is half of the thing over here, the 2x. And then the other one of these is sine squared x equals 1/2 1 minus cosine of 2x. All right, so these are the identities you need to know, like boom, 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 no thinking. All right, anything else, and there are problems where other identities are useful, but anything else is understandable if you need some time to look it up. But these ones you need to know cold. In addition to this, of course, you need to know your unit circle and your derivatives of trig functions. I'm not even going to bother going over the unit circle or the derivatives of trig functions because that's shit that I am assuming you guys are all rock solid with. If that's not the case, time to bone up. I've got resources in the review module. If you need to dig back and remind yourself what's the derivative of arctan, or what is the sine of pi over 6, or how do I find the inverse tangent of -1, all of those things you can find in the appropriate module here under the algebra and trig review. Specifically, this trig review is good. So if you need it, please don't hesitate to look back here. I want you guys to all be masters of trigonometry. It's time for this to no longer be intimidating. It's time for us to be badasses. So let's do it.
Well, Professor Faustiger, what we need to know the derivatives of like the cosecant and secant.
Yes. Yep, you got to know the derivatives of all 6 trig functions and all 6 inverse trig functions. Got to know them.
Okay.
Does this include hypotenuse?
And hyperbolic trig.
Yes.
Yeah, well, I won't be pushing hyperbolic trig. I'm happy to talk about it if you want to. Hyperbolic trig functions are beautiful, but not a required part of Calc 2 here at Santa Fe. So if you want to talk about them, I'm happy to talk about them, but I won't test you on them. But let's get into the material that I will be testing you on. So we know how to integrate the integral of sine x. This is, of course, negative cos x plus c. We know the integral of cos x. This is sine x plus c. I know how to integrate secant x and tangent x. Secant we just talked about for the first time the other day as a prereq to our odd powers of secant. And tangent you should know from Calc 1. Secant, this was the natural log of the absolute value of secant x plus tangent x plus c. And the integral of tangent can be written a few ways. It can be written as negative natural log of the absolute value of cos x. Some people also like to write this as the natural log of secant x, because that -1 can come inside the log as a power. And the kind of interplay between tangent, secant, and log is somewhat prettier with this second form, but either one is fine. Cosecant and cotangent are similar. Integral of cosecant is negative ln cosecant x plus cotangent x plus c, and cotangent is negative natural log of, oh wait, no, just regular natural log, sorry, natural log of sine x plus c, no negative on the cotangent. Okay, so these are the integrals of the 6 basic trig functions. We know how to do these. You may need to jog your memory on these ones. Right, the secant integral we just did for the first time together last Thursday as a prelude to integrating secant cubed. This was the only one that involves like a weird trick. You multiply by secant x plus tangent x over secant x plus tangent x and sub for the bottom. If you want to remind yourself how that goes, rewatch the video from last Thursday. The cosecant integral is done the same way as the secant integral. So this one and this one are both a little bit weird, and we usually just remember them. Tangent, this integral is not hard. This is a u sub problem. You write tangent as sine over cosine, and you substitute for the bottom. Cotangent, same thing. You write cotangent as cosine over sine, and you sub for the bottom. So we have these basic integrals. And the question is, what if I start mashing together trig functions? How do I integrate sine squared times tangent? How do I integrate cos cubed times sine to the third? That sort of stuff. And basically what we're going to do to figure out more complicated integrals, I'm going to break them down into a few cases. So moving here. It turns out most all combinations of trig functions can be split up into pieces that look like powers of sine. So sine to the m x times cos to the n x, or powers of secant to the m x times tangent to the n x. So if you give me some big nasty rational combination of sines, cosines, secants, and tangents, even cosecants and cotangents, I can split them up into things that look like this, plus or minus things that look like this. So our goal is just a consequence of the reciprocal identities, right? That tangent is sine over cosine, that secant is 1 over cosine. So if you take any rational combination of sines, cosines, secants, and tangents, you can write them as stuff that looks like this plus stuff that looks like this. So our goal is to be able to integrate things that look like sine to the m of x times cos to the n of x dx for any integers n and m, and secant to the m times tangent to the nx, again for any integers n and m. If you can do that, then you can do pretty much any trig integral. We're going to break these down into further cases, right? So I'm going to look at these integrals first, and I'm going to categorize them according to the parity, that is the even or oddness of the numbers m and n. So this first group of integrals I will call sine cosine integrals. The second group of integrals I will call secant tangent integrals. And what we're going to do is we're going to look at the even or oddness, the parity of the powers. And that's how we'll break it down. I will give you a strategy for these guys, and I'll give you a separate strategy for these guys. So let's begin with the sine cosine integrals. And let's begin with an example. This doesn't require anything you don't already know. Okay, I'll tell you that's true for this whole section. Everything in this section is stuff you already know. You just have to think about it a little bit more carefully than maybe you're used to having to. So if I ask you to integrate the second power of sine times the third power of cosine, sine squared times cos cubed, I claim that you can do this with u sub. You just have to be clever about it. The powerful tool here is the Pythagorean identity. And the useful feature of this integral is the odd power. The fact that there's an odd power is what is going to allow me to use u sub. Here's how we do it. Sine squared, just chilling. Cos cubed, I will write as cos squared times cos, like so. We all agree that cos cubed of x is cos squared of x times cos of x, right? If I wanted to substitute z equals sine x, this is the piece I need to soak up my differential, dz. substituting z equals sine x would be really useful if I could rewrite everything over here in terms of the sine function. If I couldn't rewrite everything over here in terms of the sine function, then fuck that substitution. It's useless, even if I have the piece I need for the differential. But the magic of this having been an odd power of cosine is that when I peel one of them off, I'm left with an even power. Any even power of cosine can be rewritten in terms of sine using the first Pythagorean identity. By the first Pythagorean identity, cos squared x is the same as 1 minus sine squared x. And when I look at this integral now, it's begging for the substitution z equals sine x. Z squared, 1 minus z squared dz. This will become a polynomial if I substitute z equals sine x. So that's precisely what we do. We calculate our differential. If z is sine x, then dz is cosine of x dx. Please don't get sloppy on this shit. Do not skip writing the x. Do not skip writing the dx. Okay, please write everything. I don't want to have to read your mind, and other people down the road will not be able to read your mind. They'll wonder what the hell are you writing if you leave things off. Here's the miracle, right? This piece is dz, and this piece will be a polynomial. And polynomials are easy to integrate. Specifically, if z is sine x, then sine squared is z squared. And 1 minus sine squared is 1 minus z squared. And cos x dx is dz. So this is the game. With sine cosine integrals, if there is an odd power, then you can transform the integral into a polynomial by making the appropriate substitution and using the Pythagorean identities. And they all go like this. From here, we'll distribute, integrate, and back substitute. So it's just a U sub problem, and it's not even a bad one. If I distribute that z squared, I'll get integral of z squared minus z to the 4 dz, whose antiderivative is z cubed over 3 minus z to the 5 over 5 plus a constant. And finally, I go back to my original variable by back substituting. So z cubed is sine cubed x, so that'll be sine cubed x over 3 minus z to the 5th is the 5th power of sine x over 5 plus a constant, and you're done. Not too bad, right?
I was wondering if there's any strategies for determining which trig, rule you should use, because just looking at this problem, I would have used the sine squared times cosine squared equals 1, because that's the most blatantly obvious. But
Well,
that probably would have led me astray.
We got to be careful. So sine squared times cos squared isn't 1, right? Sine squared plus cos squared is 1.
Oh, yes.
And that is what I used here to rewrite cos squared as 1 minus sine squared. So that is the identity that's useful here, is that Pythagorean identity. I'll come in here.
Okay, that's fair.
So since sine squared x plus cos squared x equals 1, we can deduce that cos squared x is 1 minus sine squared x. And that's exactly what we used here. There are some product to sum identities where you take a product of two trig functions and you're able to write that as a sum of other trig functions. And there are some problems for which that's useful, but those are more challenging problems. We will get to those later. Any questions on well, let me go a little further with Ethan's question there. So how did I know what to do? Right, what was the giveaway? That this was the path? It was the odd power. It's the fact that there was an odd power in either of these. Since the power of cosine was odd, I had a copy of cosine to set aside, And what's left over would be an even power. Any even power of cosine can be rewritten as a sine. So the cos squared, I can rewrite as 1 minus sine squared. And that gives me a bunch of stuff that only has sines, no cosines, times exactly the thing I need to substitute z equals sine x.
If that had been cos to the fifth, would you have split it into cos squared x, cos x, and then done the trigonometry twice?
Yep. Yeah, or I could write it as cos squared squared times cos. And then that would be 1 minus sine squared squared times cos, which is the same thing as what you're saying. Yeah. So let's look at one more of these. What did I do last time? Cosine was odd, right? Okay. So how about sine cubed times cos to the 2021? Here both powers are odd, but one power is much larger than the other. This could be attacked two different ways. I could set aside a copy of cosine with the differential, which would leave me with the 20/20th power of cosine, which is an even power, so it can, in theory, be rewritten in terms of sine. And that would lead me towards substituting z equals sine x, just like we did in the last problem. Let me show you what that looks like. Let's try the same thing. So I'd say, okay, this is integral sine cubed x times, I'll split up the odd power of cosine as 20/20 and 1. And this sets me up for the substitution z equals sine x. In order to make that substitution go through, I need to rewrite cos 20/20 as a power, as a combination of sines. So I'd begin by writing this as cos squared x raised to the what? What's 20/20 divided by 2? Well, it's 1010, right? And then I still have my cos x dx here. And now I can use the Pythagorean identity. So I'll have integral sine cubed x times cos squared is 1 minus sine squared x. And all that's being raised to the 1010th power. And then I've got cos x dx. And at this step, I can make the substitution z equals sine x. dz is cos x dx. So my integral will become integral z cubed times 1 minus z squared to the 1010 times dz. From a theoretical perspective, this is not a hard integral, but from a practical perspective, this kind of sucks. Why does this kind of suck?
Because raising a binomial to the 1010th power is pretty awful.
Yeah, I wouldn't mind squaring this out. I wouldn't mind cubing this out. Multiplying 1 minus z squared by itself 4 times is starting to get on my nerves. 5 times, I'm like, okay, I'll use Pascal's triangle. 6, 7, 8, 9, 10 times. No, I don't want to do that. That's something you give to a grad student and say, come back in a week when you've done the computation. You know, this is something you hand off to someone you want to torture. It's not pleasant. It's not pleasant. This expression right here, raised to this power, is a big long sum, and it's going to take a long time to multiply that out. So basically, on the one hand, yes, this is a polynomial, but fuck this noise. All right, I don't want to deal with that. It's big, it's huge, it's this massive long thing that you have to expand out before you can distribute the z cubed and integrate. So is there something else we could try?
Integration by parts.
Yeah, well, maybe I could do some IBP, but let's think along the same strategic lines that we were thinking in the previous problem. There's something that's very similar to what we did on the previous problem that we could do here that doesn't suck the way this sucks.
Can we do sine squared x times sine? And
Yeah,
then cosine
right.
squared x times cosine 2019 x.
Beautiful. Yeah,
Yes.
exactly. Daniel and Matthew are both right on the money with this. Both of these powers are odd. In the last problem, only the cosine power was odd. So I kind of had to start by peeling him off and substituting for sine. Here, since the power of sine is odd, I could split this up the other way. I could say, okay, I'm going to split this up as sine squared x times cos 2021 x times sine x dx. And then instead of rewriting the cosines as sines, I can rewrite the sines as cosines and substitute for cosine. So sine squared, that's 1 minus cosine squared x. That's that first Pythagorean identity again. Cos to the 2021 x, I just leave that. And my differential at the end here, sine x dx, I'm going to group those together because I'm going to substitute for cosine. So instead of substituting for sine, I substitute for cosine, that's all. So here, if I make the substitution, z equals cos x, then dz will be negative sine of x dx. So this piece, instead of being dz, will be negative dz. That's not bad. And again, I'll be left with a polynomial. This time, though, the polynomial will be easier to work with. I'll have integral 1 minus z squared times z to the 2021 times negative dz. Right? If dz is negative sine x dx, then sine x dx is negative dz.
We can pop the negative out, right?
The negative pops out. Yep. So I always like to write this like I am here at the parentheses so people don't get confused. Otherwise, it kind of looks like subtraction. This is negative 1 times dz. So the constant factor of negative 1 pops out. And I'm left with negative integral 1 minus z squared times z to the 2021 dz. And this is much easier than this. Here, I have to FOIL out 1 minus z squared to the 1010. That's awful. Here, I just have to distribute this across these terms. So I get negative integral z to the 2021 minus z to the 2023 dz. And now we're ready to integrate. So my antiderivative here, I'll put the negative out front, bracket z to the 2022 over 2022 minus z to the 2024 over 2024 plus c. And then we go back to our original variable. I'll distribute the negative while we're at it. So this will be negative cos 2022 x over 2022 plus cos 2024 x over 2024 plus a constant. So while we could manage it the other way, this is much nicer. And both answers would be correct. So I would prefer to do this. Easy choice.
So basically, whenever there's like two odd, like we have sine and cosine, they both have odd powers, we should pick the smaller odd power to separate.
Yes.
Okay.
Yeah, so we're kind of getting close to being able to write down a general strategy for these. If there's only one odd power, if you're doing a sine cosine integral and only one of the powers is odd, then you're going to substitute for the function who has the odd power. And the way, well, then you're, sorry, I should say this more carefully. If only one of the powers is odd, like the previous example here, you're going to grab one of these and set it aside with the differential and substitute for the other guy, substitute for the even function. Once you grab one of your odd powered guys and set him aside, what's left will be an even power, can be rewritten in terms of the other function, and then you substitute for that other function. If both powers are odd, then the smart move is to set aside not one of these, but one of these, one of the smaller guys. So you can substitute for the larger powered function. You'll rewrite the remaining pieces using the Pythagorean identity, and the result will be a polynomial. Polynomials are easy to integrate. So you guys tell me, in the sine cosine integrals, what case have we not handled yet? We talked about one odd power, both powers odd. What's missing?
Two even powers.
Inverse.
Yeah, and what if neither powers are odd? If neither power is odd, that means both powers are even. Simplest examples of these are just the integral of sine squared or the integral of cos squared. Here, the power of cosine is 0, which is even, right? 0 is divisible by 2. So this does live in that category of both powers are even. It's just the very simplest possible case there. If there is no odd power, then I can't play that game, right? Where I set one copy aside and substitute for the other guy and use Pythagoras. There's really none of that I can do. But if you think back to that list of identities, one of these is tailor-made for this shit. The bottom right, sine squared equals 1/2 times 1 minus cos 2x. Gets rid of the power, gives me something I know how to integrate right away. So here we will use these are called half angle identities. And what I get is integral of 1/2 times 1 minus cosine of 2x dx. So this is a manageable integral. I can pop the 1/2 out, and then I just need to integrate 1 minus cos 2x. The 1 is easy to integrate. The cosine of 2x is a little micro u sub, right? It's one of those tiny little u subs that we should be getting good at doing quickly in our heads. So my antiderivative here is x minus, what is an antiderivative for cosine of 2x?
Sine x over 2.
Sine of 2x over.
Yeah, that's what I meant.
Yeah, good, good. All right, yep. So you know that the integral of cos 2x should be sine 2x. And then you're like, okay, well, if I differentiate sine 2x, I would get 2 cos 2x by the chain rule. So instead, I need to have sine 2x, and I need to divide by 2. This is one of those micro u subs. And that's it, you're done. Easy as pie, right? Not bad. Cos squared goes the same way. So what about sine squared times cos squared? Well, it turns out it's the same shit. Sine squared, I'll replace by 1/2 1 minus cosine of 2x. I'll use the half angle identity for him. And cos squared, I'll replace by his half angle equivalent, which is 1/2 1 plus cosine of 2x. In general, this is how you handle even powers. If both of the powers are even, if there is no odd power, you just replace everybody by their half angle equivalents and you bash the thing with the algebra hammer until it looks nice. These tend to be the least fun. The 1/2 times 1/2 can come out as a 1/4, and what's left inside is 1 minus cos 2x times 1 plus cos 2x. And I beg you, please be careful with your parentheses here. Parens can make all the difference when it comes to reading these and actually telling what's going on. So please put the inside of your trigs in parentheses, like the 2x here. Put any quantity in parentheses. Just, respect the notation and you'll be fine here. I'll distribute and get 1 plus cos 2x minus cos 2x, those cancel, minus cos squared of 2x dx. Now the 1 I know how to integrate, but how do I integrate cos squared of 2x?
Would you run it through its trig identity, or would you just start this process over?
Yes to both, right? So this process was a trig identity process, and while we have other identities we could apply, the trick to integrating cos squared of 2x is going to be to again apply a half angle identity. So let me just really quick copy these half angle identities that we're using over here. They are sine squared of x equals 1/2 times quantity 1 minus cos 2x, and cos squared of x equals 1/2 1 plus cos 2x. I kind of think of these as if you remember one, you get the other for free, just change the plus to a minus. So what about cos squared of 2x?
The angle in like on the other side of the right side would be 4x.
Very good. Right? The thing that's over here is just double the thing that's in here. This could be cos squared of dog shit, and I would get 1/2 1 plus cosine of 2 dog shit. So if this is cos squared of 2x, I get 1/2 1 plus cos 2 times 2x, which is 4x. So that's what I'll use here. You could split up the integral and do the integral of 1, but it's better to wait until you've done this, because you'll have some constant terms that you can combine. So I'll have 1 minus 1/2 1 plus cos of 4x dx. Again, careful with the parentheses. Now I'll distribute the 1/2. He goes here and here. And I get 1/4 integral 1 minus 1/2 minus 1/2 cosine 4x dx. And now everything in here I know how to handle. I can combine these two. 1 minus 1/2. That's just 1/2. We get all together 1/4 integral of 1/2 minus 1/2 cosine 4x dx, like this. And now we're to a place where I know how to integrate all the things. An antiderivative for 1/2 is 1/2 x. And then an antiderivative for cosine of 4x is sine 4x over 4. So I'll write this as minus 1/2 times sine 4x over 4. These are being multiplied. And then we slap on our plus c at this stage. If it is polite to distribute the constants. So this is 1/8 x. The 2 and the 4 here will make 1/8, and then the 1/4 here will make 1/32. So minus 1/32 sine of 4x plus a constant. And this is how you handle all of the sine cosine integrals where all the powers are even. You just use those double angle or half angle identities and you bash the thing to death with algebra and half angle identities until you get stuff you know how to handle. Questions on this problem?
Yeah, I had one.
Yeah.
So the second step, now the third step that you have on this page, yeah, there. It would make it a lot harder if the powers weren't just 2 and 2, right? Because you would be able to just LOL that out. So what would it look like if you had,
Yeah,
like,
if this was like a 20, then you're in rough shape. Unfortunately, there's no like cheat codes here. If these powers were larger, like 4 and 4, or even like 6 and 4, or 2 and 4, things get pretty unpleasant. But this is the method. This is all we got. I'm not aware of any ways to readily handle these integrals when the powers are both even and quite large. As that happens, these just do get more unpleasant. Good practice problems here. The combined degree should be like no greater than 6. Yeah, so like if the sum of the two powers is greater than 6, then you've run into a nasty problem. They're still handled the same way. This is, you feed it to Photomath, Wolfram, Bartleby, whatever you want, it'll all tell you the same shit because this is really the only nice way to do it, short of tricks using complex analysis. So, if the combined powers are like 2, 4, 6, that's manageable. If it gets bigger than that, then you're looking at nasty stuff. But you would attack it the same way. You just have to be patient.
So like if it was like sine to the 4th power instead of instead of sine to the 2nd power, would you do like sine squared raised to the 2nd power and then like do
Yep.
the half angle in there? Okay.
Yeah, let's finish this up by at least setting up one more with these even powers. I don't know if I want to spend the class time to work this all the way, but let's take a look. So let's pretend like this is just sine to the 4 of x dx. Then my starting move here would be to say, okay, you can write it as sine squared x times sine squared x, or you can write it as sine squared x squared, same thing. And then I would use my half angle. So that's 1/2 times 1 minus cosine of 2x all squared, which is 1/2 squared times 1 minus cos 2x squared. So 1/4 will pop out and you get integral of 1 minus cos 2x squared. And then you FOIL it out and proceed from there. We might as well do it. This would be 1/4 integral 1 minus 2 cos 2x plus cos squared 2x dx. And then the cos squared of 2x piece is going to get that same clever half angle treatment where I say, okay, since cos squared of x is 1/2 1 plus cos 2x, cos squared of 2x must be 1/2 times 1 plus cos 4x. So this would be 1/4 integral 1 minus 2 cos 2x plus 1/2 1 plus cos 4x dx, and then distribute the 1/2, combine like terms. And this will be 1 minus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x dx, and then this 1/2 and this 1 can talk to each other. That's 1/4 integral 1 plus 1/2 is 3/2, and then minus 2 cosine 2x plus 1/2 cosine 4x dx. And now we're ready for an antiderivative. That antiderivative is 3/2 x minus antiderivative for cos 2x is sine 2x over 2. The 2's cancel, so you'll just get sine 2x. And then an antiderivative for cos 4x is sine 4x over 4. So you'll have, together with that 1/2, 1/8 sine 4x. And then again, to be polite, we should distribute this constant. So this would be 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus a constant. So like I said, the case where the powers are all even, these tend to be the less fun problems. They're a little bit grindy. You just use the same identities over and over and over again, combining like terms at each step until you are to a place where you can see what your antiderivative is. In this problem, that's this line. So we're feeling pretty good about sine cosine integrals? A little bit, all right. Let's write down the strategy. We've now been through all the cases. Let's see if we can't take what we've really discovered here and express it in a way that communicates how to handle all of these. I'll hold here for about 5 more seconds. People are writing.
If we don't write down the plus C on the second to last step and the problem like gets on the test, would we lose credit?
Half point, half point, something like that. The plus C does matter, right? The indefinite integrals, the idea with that plus C is that your answer is an infinite family of functions, all the vertical translates. If you left it off at this line, but then added it at this line, I probably wouldn't take points off, but I would make a note. If you left it off altogether, I would take off a half point on a test. So free response questions are worth 5 points on my test, or actually 10 points on the new system. So you lose a point, right? On the new format. So if you leave off the plus C altogether, but everything else is right, that's 9 out of 10. If you skip the plus C until the end, then I probably wouldn't take off points, but I would make a little note. The idea is it's a notation thing. Technically, we need the plus C at this line because this is our first line without an integral. Once the integral goes away, the plus C needs to show up. All right, I am going to change the page now, and we are going to summarize everything we just discovered. So integrals of the form we've got a strategy that depends on the parity, and we have two cases. Your book breaks it down into three cases. I think that's silly. First case, there is an odd power, i.e. one of m or n is odd, or both. All right, this is the mathematical form. If there is an odd power, then you set aside with the differential one copy of the odd powered function. Then rewrite the remaining powers of that function using Pythagoras. Finally, substitute for the other function. I'll try to get this to focus a little better. That's it. So if there's an odd power, say cosine has an odd power, you set aside one copy of cosine with the differential. The remaining powers of cosine will necessarily be an even number because you've taken one away from an odd number. The remaining powers of cosine you rewrite in terms of sine using the Pythagorean identity. Then finally, substitute z equals sine. The other case here, there is no odd power. Both m and n are even. In this case, you just beat the thing to death with half angle identities. Which are cos squared x equals 1/2 1 plus cos 2x, and sine squared x equals 1/2 1 minus cos 2x. And be aware of alternate forms. Of this identity. Like cos squared of 2x equals 1/2 1 plus cos 4x, and sine squared of 2x equals 1/2 1 minus cos 4x. And use algebra. And micro use subs. All right, so this is it. This is how you integrate any power of sine times any power of cosine. Those integrals all fall into one of these two categories. If you're in the first category, life is good. You're going to do a little substitution. And the trick to making those substitutions work is setting aside one of the odd powered functions with the differential, rewriting the remaining powers in terms of the other function using the Pythagorean identity. If you're in the bad luck case where neither power is odd, then you just beat the things to death with these identities. You just use these identities again and again and again until you've gotten rid of all the powers. Once all the powers are gone, you can finish the problem using those little micro U subs. Not too bad, right? If you want to, I always encourage you to read the textbook. The textbook breaks these down in a little bit more detail. Sometimes I think more detail is helpful. Other times I think more detail can obfuscate what's going on. So here is their version of what we just said. If power of cosine is odd, and I say, you can write it as 2k plus 1, then you're going to save one copy of cosine with the differential and use the Pythagorean identity to express the remaining terms in terms of sine, and then substitute for sine. If the power of sine is odd, then you'll set one copy of sine aside with the differential, rewriting the remaining ones as cosines and substitute for cosine. So this is the first case. And then if both are even, cross your fingers, use these identities and get out the algebra hammer. It's true that sometimes you can make use of this identity down here at the bottom. I guess it's worth saying that. This is just a rephrasing of the double angle for sine.
That would make both even powers odd, yeah?
This has some unfortunate consequences. So if you were to if you had sine squared times cos squared, and you applied this to one copy of sine cos, then you would end up with 1/2 sine 2x times sine x times cos x, which isn't nice. Usually you want the inside of your trig functions to all be the same. So if you wanted to use this identity, you can chop things down as long as the powers of sine and cosine match. So if you had sine squared times cos squared, you could write that as this thing all squared, and then make use of the modified half angle sine squared 2x thing. But I wouldn't argue that that's any faster. And I think if you're looking for a simpler strategy, I think the less you have to memorize, the better. But I encourage you to play around. Yeah, it can knock the powers down using this identity, but you need to make sure that you use this in such a way that the inside of your trig functions all stay the same. So if you convert part of them to sine x cos x and part of them to sine 2x, you're going to need to use some other identities to either get the x's to 2x's or to bring the 2x's back to x's. Doing the latter would undo this process. So if you're going to make a conversion like this, make sure you're able to do it everywhere in the integral. But this is, playing around is the way to get good at this stuff. So play around, see what you like. But here is my suggested strategy, right? I recommend following this. The next family of integrals we're going to attack are the secant tangent integrals. But there's something I want to say before we do that. You guys heard the word orthogonal before?
Yes.
What does orthogonal
Not at all.
mean?
Orthogonal means it's a 3D perspective without using perspective.
Let's see.
Those words have no meaning to me, but I appreciate it.
All right, let me help. Orthogonal means right angle. Orthogonal means, when I say two objects are orthogonal, I mean they meet at 90 degrees. Orthogonality turns out to be a really important feature in mathematics. Think about the XY plane. The XY plane is made up of, you guys, physics is a co-rec for this class, right? You guys can take physics. How many taking physics 1 right now?
I am.
Me.
I am.
Okay, handful of folks. So you guys know what vectors are, right? So a vector is an arrow. Yeah, it's an arrow in the plane. A 2D vector is an arrow in the plane. It turns out that when mathematicians want to study mathematical spaces, and the plane, the XY plane, is a mathematical space, one of the best ways to do that is to understand it as a vector space. And that is a place where you can add, subtract, multiply by constants. and stay within your space. R2, the plane, the XY plane, is a vector space. And if you take any point, like 2, 3, in this vector space, I can think of this as a combination of the vectors 0, 1, and 1, 0. 0, 1, the vectors, we always think of them as coming from the origin and going out to that point, right? If I want to build the vector 2, 3 out of these vectors 0, 1, and 1, 0, I would take 2 copies of this vector and add it to 3 copies of this vector. These two vectors, 0, 1, and 1, 0, again, think of them as arrows who start at the origin and end at these points. So the tip of one arrow is here, the tip of the other arrow is here. Those vectors are orthogonal. They meet at a 90-degree angle, which means they form what's called a natural basis for the plane. I can build any vector, like the vector 2, 3, out of combinations of this vector and this vector, right? Like we said, multiply this one by 2, multiply this one by 3, and add them up. 2 times 1, 0 is 2, 0. 3 times 0, 1 is 0, 3. And if you add those, you get 2, 3. A basis for a space is the most useful thing you can imagine from the perspective of mathematical proof. I really like having a basis for any mathematical space I want to fuck with. One of the most important mathematical spaces in existence is the space of continuous functions. Vectors there are not arrows. Vectors in the space of continuous functions are functions. Fun trick, if anybody ever asks you what is a vector, the smart answer is an element in a vector space, not an arrow, nothing to do with magnitude or direction. A vector is an element of a vector space. Every continuous function, it turns out, can be expressed as a combination of cosines and sines. Sines and cosines are orthogonal, meaning they are in some sense perpendicular. Now, what does that mean? It's an abstract concept. Obviously, they're not arrows. I can't talk about the angle at which they meet in any intuitive way. But there is a way to define the angle between two functions. It's done in terms of an integral. And the fact that sine and cosine are orthogonal means that their dot product in this, abstract vector space of continuous functions is 0. And if these terms don't mean anything to you, it's okay. Once you learn a little bit about vectors, you'll understand what I'm talking about. Sines and cosines being orthogonal has a consequence. The notion of dot product for these functions, so here, quick note. The inner product, aka dot product, if you've studied vectors, you know what a dot product is. If you haven't studied this stuff, don't worry about it. You don't even have to write it down. The inner product of two functions is integral from negative a to a f of x times g of x. All right, this is what we call the dot product of f and g. It's usually written like this, sometimes written like this, but people confuse this with other things, so we don't usually write it like that. In practice, we usually take the complex conjugate of the second function, because usually we allow these to be complex valued functions. And in practice, we usually use pi and negative pi as the bounds for the integral. The fact that sine and cosine are orthogonal, right? So two objects are orthogonal if and only if their dot product is equal to 0. So here, f and g are orthogonal functions, means that the integral from negative pi to pi of f of x times the complex conjugate of g of x is equal to 0. And a neat fact, sine mx and cos nx are orthogonal. So this is just a little bit of something fun for those of you who are taking physics and are learning something about vectors right now. Turns out vectors can be a lot more than just arrows. A chair can be a vector in the appropriate vector space. One of the most important vector spaces, especially if you're interested in quantum physics, is the space of continuous functions. When you're studying the space of continuous functions as a vector space, the natural dot product turns out to be this integral. And your basis vectors are sines and cosines. Sine and cosine are orthogonal as long as their frequencies are different, meaning as long as m is not equal to n, this dot product will always come out to 0. So fun fact, I will talk more about the significance of this stuff and Fourier series a little bit later in the semester. This turns out to be how you get the coefficients for Fourier series, which is really the basis expansion of an arbitrary function in the basis of sine and cosine. So those of you interested in going deeper into mathematics or any sort of linear algebra or quantum physics related fields will be using the shit out of this stuff down the line. Anyway, it's enough of that digression. The man who discovered that, by the way, Joseph Fourier, Frenchman, trying to figure out how heat dissipates through a plate, trying to solve the related partial differential equation, discovered the orthogonality of sine and cosine, which started a whole field of mathematics called harmonic analysis. This is just a little over 100 years ago. So now we're ready to talk about integrals of the form power of secant times the power of tangent. And the strategies here are not all that different than the strategies we met relating sines and cosines. What made the sine cosine stuff work, especially that first strategy? Two factors. The Pythagorean identity relating even powers of sine to even powers of cosine. And we have that same thing with secant and tangent, right? Even powers of secant can always be written as tangents. Even powers of tangents can always be rewritten as secants. The other thing that we needed to make that strategy work for sines and cosines was the fact that the derivative of sine is cosine, and the derivative of cos is negative sine. Here, secant and tangent are not quite that nice, but they're not a lot worse. So again, we'll be considering different cases, and I want to begin just by looking at a couple of integrals. Imagine I want to integrate secant to the fourth times tangent to the fifth. I claim that this can be done in a manner very similar to the odd power case for the sine cosine integrals.
You would use the tangent secant equivalency rule, yes?
Yes. So the main tool here, the thing to be keeping in mind, is the second form of the Pythagorean identity, tan squared plus 1 is equal to secant squared. The long-term goal here is to make a substitution. And the trick is thinking about the derivatives. So you know that you've got this identity. This is going to be useful. You also know that the derivative of tangent of x primed, is secant squared x, and that the derivative of secant is secant x tangent x. So let's think about what we can peel off and set aside with the differential, such that what's left over will be nice and easy to rewrite in terms of the other trig function. If I set aside two of the secants, then I can rewrite the remaining secants in terms of tangent, and the piece I need to substitute z equals tan x is sitting right here. Secant squared, that's tan squared x plus 1. So I'll have tan squared x plus 1 times tan to the 5th times secant squared x dx. If I substitute z equals tangent x, then dz is secant squared x dx. This piece will be dz, and this piece will become a polynomial. Specifically, it'll become z squared plus 1 times z to the 5th dz. So similar to the sine cosine thing.
Didn't you tell us that we should first start these sorts of problems by breaking apart the odd exponent one?
So similar to the sine cosine one, but not identical, right? There are
Okay.
differences here. So we're going to have a different strategy, but in spirit, it's similar. What I mean by that is our long-term goal is to make a U sub, and the tricks that get us there are the Pythagorean identities. But it's true that,
Okay.
yeah, now it's not just about like even odd. It's a little more complicated.
And so we'll be expanding upon these more in like Thursday's class, right?
Yep. Yeah. Give me a few minutes here, and I'll give you a general strategy, just like we had for sine.
Cool. Sorry.
No, you're good. You're good. So now I distribute my z to the 5th, and I get integral z to the 7 plus z to the 5 dz. Find our antiderivative, which would be z to the 8 over 8 plus z to the 6 over 6 plus a constant. And that z to the 8 is tan to the 8. And this z to the 6 is tan to the 6. And c is c. So this one, not so bad. And the thing that made this go was the power of secant being even. If the power of secant is even, like secant to the 4, then you can grab two of them, set with the differential, and you'll have an even number of them left over. When you take 2 away from an even number, you always get another even number. The remaining even powers of secant can always be rewritten in terms of tangent. So you'll end up with a polynomial in tangent times the thing you need to substitute for tangent. So that's what we do. We substitute for tangent, and then we get a polynomial and we integrate. These are not too bad. So if the power of secant is even, we're Gucci. Does anybody see another way we could have attacked this problem?
Integration by parts.
Again, IBP maybe. It is a product, so we could try. but it's not going to be super easy. Does anybody see another way, kind of in the spirit of the things we're doing, that we could have attacked this?
U sub for secant, because secant tangent is the derivative of it.
Good, very good. So Daniel makes a comment here. You can turn everything into sines and cosines. That's also an option. And if you're really having trouble with one of these and nothing is working, turning everything into sines and cosines is a viable attack. But I really like, who was it? Was it Alexander's suggestion of trying to substitute for secant? So here we substituted for tangent. Let's see if we can do this same integral by substituting for secant. So I'm going to rewrite this thing, and then we'll discuss what makes it go. All right, I'll give you just a second in case anybody is writing this. All right. So same problem. Integral secant to the 4 times tangent to the 5th the derivative of secant is secant tangent. So if I want to substitute for secant, I'll take one secant and one tangent and set them over here with the differential. Then rewrite the remaining tangents as secants. So I'll have secant cubed times tan squared squared, that's tan to the 4, times secant x tangent x dx. And then tan squared is secant squared of x minus 1. And that's coming from the Pythagorean identity. Tan squared x plus 1 equals secant squared x. So if you subtract 1 from both sides, you get tan squared x equals secant squared x minus 1. I'm getting a very strange phone call here. 1 second. Hello? Hello? This is Professor Fausticker. Hello? Nope. All right, they hung up. Okay. So instead of substituting for tangent, which required setting aside a copy of secant squared, I can try substituting for secant, because when I set aside a copy of secant tangent, I'm left with an even power of tangent, which I can rewrite as secants. So from here, I could sub z equals secant x, because dz is then secant x tangent x dx. So this piece would be dz, and this piece will be a polynomial. Specifically, z cubed times quantity z squared minus 1 squared, and then dz. And now the same sort of shit. We'll FOIL this out, distribute the z cubed. That's z to the 4 minus 2z squared plus 1. So the polynomial you integrate is z to the 7 minus 2z to the 5 plus z to the 3 dz. And your antiderivative is z to the 8 over 8 minus 1/3 z to the 6 plus 1/4 z to the 4 plus c. And then we go back. So this will be the 8th power of secant x over 8 minus the 6th power of secant x over 3 plus the fourth power of secant x over 4 plus a constant. So this is an integral that can be attacked two different ways. Kind of like the case where these sines and cosines were both odd. On this particular integral, I prefer our first solution. I prefer substituting for tangent because I didn't ever have to square out a thing like this. I didn't ever have to do that algebra. But they both work. And if we want to write down a strategy, we have to figure out what makes those work. And then we'll look and see if there are any cases that are outside. Now, where am I? This is about 12:30 to 1:45, right? So I think I've gone over by a few minutes. So let me hold here. All right, we will stop here and resume exactly at this point next time. Between now and Thursday, I would like you guys to think about a strategy for the secant tangent integrals. In terms of the parity of m and n. We saw that if the power of secant is even, there's something we can do. I'd like you to try and identify what allowed this to work, right? So he said if m is even, then we can sub for tangent. What is the condition under which we can sub for secant? And then are there any integrals of this shape, secant tangent, that are outside of those two cases? And you can read the textbook, of course. The textbook has the answer to this question and the other one. But I think it's fun to discover these things yourself, right? There's nothing quite like making a conjecture and then discovering that you're right, or making a conjecture and fighting to prove that you're right, or making a conjecture and then discovering that you're wrong, but also at the same time learning what is right. So think about this question. See if you can come up with a strategy, like the strategy we wrote down for the sine cosine integrals, that always works for these secant tangent things. I have to warn you, there's a nasty case hiding in here. The secant cubed integral falls into this category, doesn't it? That's where the power of secant is 3 and the power of tangent is 0. And that doesn't yield to any of these sort of methods, right? That one requires integration by parts. So lurking somewhere in these possibilities of the power of secant being even or odd, the power of tangent being even or odd, lurking somewhere in there is a category of integrals that are hard. Secant cubed belongs to that category. So see if you can identify the two nice categories and the one hard category. And then on Thursday, when we get together, I will show you exactly what those are. I'll give you the most general strategy that exists, and I'll show you how to handle the hard ones in general. And the answer to those is integration by parts and crossed fingers. But yep, that's it. This is where I'm going to leave you guys for today. You do have a new homework set that's open, so please take a look at that. It should be open just now or just within the last few minutes. And of course, last week's homework has come due, so if you need more time on that, submit an extension request. I did go in and clear everything that was there this morning, but if you requested something since then, or if you need more time but haven't requested, please take a look, knock that shit out, and I will go back and clear them one more time before the end of the day today. That's all I have for you guys now. The only other thing I would say in parting is that test 1 is coming. Test 1 is not too far away. After we finish section 7.4, we will be preparing for test 1. So this is section 7.2, which means the end of next week is probably going to be when we're ready for test 1, which means test 1 will probably not be next week, but the following week. So that kind of part of the beginning of the semester where you can be like lighthearted and not really giving a fuck and like kind of not spending time on math every day is over. It is time to be working hard. Get ready for test 1. It tends to be a rough kind of wake up call in this class. I want you guys to have a good experience, so please make sure you're sinking time in, come to office hours, work the homework, and ask for help if you need it. Anything before I let you go?
No, just have a great day, Professor.
Thanks, Ethan. Any other questions?
Can I say the one where you solved it the other way? The
Yeah.
secant? Yeah, I just want to
Yeah,
take a
we want to
picture.
come back to the other solution of the secant tangent integral here. I think
Yeah.
this one is easier. I prefer substituting first tangent here. This is
So I'm assuming there's gonna be one where like secant is odd, right? There's gonna be a case where it's odd instead of even.
so yeah, definitely in both of these, right? These were the same integral. The power of secant was even and the power of tangent was odd. The even power of secant, we said, is what makes this work.
Mm-hmm.
The odd power of tangent is connected to the other technique. And then there is a third case outside of those. So if the power of secant is even, you can substitute for tangent. If the power of tangent is odd, then as we did here, you can substitute for secant. And if neither of those are true, then you're in the rough case. But we'll talk in detail about that on Thursday.
Okay. All right. Thank you.
Of course. Yeah, any other burning questions before I let you guys go for the day? Alrighty then, I hope you guys have a lovely rest of your day. Work hard on math between now and Thursday, and on Thursday, we will do more trig integrals. Have a good evening.
All right. Have a good day.
Thank you.
You too.